Good afternoon, and welcome to today's Machine Design webinar. This webinar is titled The Benefits of Roller Screw Technology in Electric Actuation, sponsored by XLR. I'm Carlos Gonzalez, Technology Editor with Machine Design. Let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Today's event will last about 30 minutes. We will hear from our speaker for about 25 minutes, and the remainder of our presentation will be dedicated to a Q&A session. We welcome your questions during today's event. Just type your question into the question window on the side of your screen and then hit the submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. Please also be aware that today's session is being recorded and will be available on the Machine Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking the green folder icon in the toolbar beneath the slides. Let me now introduce today's speaker. Mike Wolf holds a critical position as our Technical Services Manager. Mike provides leadership for our customer service, applications engineering, and returns and repairs departments. He received a BS degree in business from St. Mary's University of Minnesota and an AAS degree in automated manufacturing systems from Dunwoody College of Technology. Mike has 15 years of experience within the factory automation motion control industry in both technical and leadership roles. Mike is well regarded in the industry. Now let me turn things over to our presenter. Mike, the floor is yours.
Well, good morning, everybody. Thanks for joining us. I'll be talking over some of the benefits of the roller screw technology and electric actuation today. So I'll get started here. First off, we'll go through some of the types of roller screws that are available. We'll get into a little bit of a compare and contrast between a roller screw and a ball screw. We'll go through the roller screw electromechanical actuator packaging design considerations, and then taking a look at some of the differences with an inverted roller screw style electromechanical package. So roller screws, what are they? They're a very high efficient, high load capacity rolling contact rotary to linear conversion device. So effectively we're taking rotary motion from a turning shaft and converting that through a screw into a linear motion. We have basically a very large contact area because there's multiple threads that are touching at any given time to be able to ultimately lower the contact stresses, translating them across multiple points, resulting in a longer life and a higher load capacity for the package size. First off, I'll go over a common planetary roller screw. This is what we typically call the conventional design. It's a long helical threaded shaft, a very short helical threaded nut, which is the outer rolling piece, and then helical threaded rollers, which act as kind of planets within the nut to be able to roll along the shaft. The rollers act in a similar manner to, if you're familiar with a planetary gearhead, you're having the gears rotate around a shaft, in that case a sun gear, translating different energy out of the shaft. In this case, we're taking that same concept, gearing these rollers, timing them to be able to have coordinated motion around the shaft, but we're not reducing. We're just providing a one-to-one planet around the shaft. So the thread profile is what gives us the amount of distance that we travel within one revolution of the roller screw. So the next type we'll go over here is a recirculating style roller screw. These are a little bit less common in the industry. They also have a long helical threaded shaft, the short helical threaded nut. But in this case, we have an annular grooved roller, which has kind of a convex roller profile, which allows these rollers to recirculate. They're going to drive down the path as the nut is rotating, and then they're going to cross over to the next set of threads as they go. So there's no need for any type of gearing. Next type we'll go over is the inverted roller screw. This is a little less common. It is a long helical threaded, internally threaded cylinder, a short helical threaded, external threaded shaft, and then it also has the helical threaded rollers. In this case, rather than having a long threaded shaft, we have a very short shaft using the same style of a roller to be able to connect to that long threaded nut, if you will. We're basically inverting it, so the length of the roller screw is created by the long threaded cylinder versus the short roller screw. So in this case, we still have the planet action of the rollers acting as the connection point between the internal thread and the external thread. So when we take a look at some of the similarities and in a compare and contrast from a roller screw to a ball screw, we have basically the manufacturing techniques of making a ball screw and a roller screw are typically very similar. The materials that are being used, the hardnesses that are being used of these materials, the processes of finishing the shafts and components are typically going to be used, similar processes in grinding the components, and also other potentially using thread rolling or thread milling in creating the long threaded shafts. With regard to precision or lead error, common lead error for both types of technologies is class 5, but we can also, in special situations, very high precision can be possible down to 6 micron per foot, or 300 millimeter. With regard to efficiency of the translation of the rotary motion to linear motion, typically you're going to find between 85 and 92% efficiency for both types of technology, depending on what lead you're using. It affects it slightly. So if we look at the differences between a roller screw and a ball screw with regard to load path, the roller screw is going to have a profiled roller that's going to have that convex thread profile and the splined ends or the geared ends for the timing. The lead precision is going to be dependent on that load path, so there's going to be both a V profile on both the shaft and on the follower. Whereas when you look at the ball screw, you're going to have more of an arched profile or a radius, depending on the design of the ball screw. And then a round ball is going to be providing that contact point within each thread, so to speak. So when we look at the contact radius difference between the roller screw and the ball screw, you have the ball, which is when you take an example of a 30 millimeter roller screw or a 30 millimeter ball screw, here in the lower right, we have a little example of the size of a ball in comparison to the size of the roller thread. So you identify that you have a profile radius of 1.75 millimeters for the ball versus 2.5 millimeters for the roller contact. So we end up having a mean contact radius of 3.5 millimeters, which is effectively twice the contact radius due to the number of contact points there. So again here with the roller screw, you're going to typically have higher contact radius with a steeper lead, with a finer lead, because there's more contact points. With a ball screw, again, it's going to be smaller contact point with the finer lead. So typically, you're going to find that a roller screw is going to have many more benefits at the finer lead because of those contact points relating to higher load capacities due to those number of contact points. Whereas with the ball screw, they're going to have the higher contact points with the steeper lead, which is typically why you see the steeper leads on the ball screws. So when we look at the number of contact points, the roller screw is always going to be greater because it's not limited by the ball diameter. Typically, when you're looking at the roller screw, you have 10 planetary rollers. You're going to have 5 contact points on each roller, so you end up with 50 individual contact points over one axial lead of the lead. Whereas with the ball screw, you're limited by the size of the ball. The ball is always going to be around 70% of the lead. So you end up with just slightly over half the number of contact points within any axial lead length. So when we look at dynamic and static load ratings, the roller is typically going to have a higher static and dynamic load rating when you're comparing the same diameter screw and lead. And this is, again, due to the higher number of contact points, the larger radius, the overall stress, contact stress on the rolling elements ends up being much lower because of that. And it also provides the additional ability to have a higher resistance to shock load due to the number of contact points. So the ball screw is limited by its available space to hold the recirculating balls, and again, by the ball diameter there. So ultimately, your normalized contact stress is going to be lower in the roller screw, effectively based on those number of contact points there. So when we look at the relationship of diameter to speed, the rated speed of a ball screw is typically, in this case, a 30 millimeter ball screw with a 5 millimeter lead is going to be half the speed, rated speed of a roller screw. Typically, the speed limitation is going to be due to the ability for the ball screw to recirculate, conflicting friction, and some ballistic collision that's going to occur. So if you take your diameter, your common diameter of 30 multiplied by your speed, you end up with a much higher value to be able to produce both high force at high speed. So when you take into account that in some cases a ball screw may be able to get higher lead because the balls allow for a much steeper lead than you're going to be able to create with a roller screw. You could use a roller screw with a finer lead, but because it's going faster, you're able to produce the same amount of force for a lower amount of torque when you're comparing two application or two of the same application with ball screw and roller screw. So for the roller screw, the ability for the screw itself to allow for contamination tends to be higher with the roller screw because you have the multiple points of contact when comparing with the ball screw, and the timing gears. You don't have the the requirement for the balls to roll around. Any kind of contamination that gets within that ball nut is limiting the ability for the balls to continue to recirculate. So you end up having a kind of a snowballing effect of potential for damage or locking up of the ball screw, whereas a roller screw can take very small imperfections or small contaminations and effectively go right through them without having to have the binding process. And so it would require some severe contamination or damage to be able to jam up a roller. With regard to maintenance, the roller nut can be completely removed without any kind of parts falling apart. There isn't a pre-assembly. The nut is actually an assembly on its own, so it can be screwed right onto the shaft to be able to be cleaned and re-lubricated and reassembled. With the ball screw, you're looking at individual balls. Once the nut is removed, they have to be carefully reassembled and ensured that everything is kept clean and you don't have any loss of the components necessary to properly reassemble. With regard to maximum lead, roller screws typically, I think I alluded to earlier, they typically prefer the finer leads. This is basically due to a limitation of the ability to manufacture the threads at a very high angle. So cross-threading mesh of roller with the screw is more difficult with the longer lead. So the thread starts to the diameter ratio. There's a requirement of that each roller screw is going to have a multi-start thread, so there's thread after thread after thread. So in the case of a 30 millimeter roller screw, a 30 millimeter lead becomes a very difficult process to maintain and be consistent. You end up with potentially higher scrap rate when you start getting to the point where the ratio of the lead to the diameter of the screw becomes close to the same. So a 20 millimeter lead tip tends to be more practical. Whereas in the case of a ball screw, you don't have the limitation of the roller thread meshing. The greater than a 30 millimeter lead can be possible with a ball screw. But the opposite is true when you go into the smaller leads. When you go into the smaller leads with a ball screw, you tend to have smaller and smaller balls. What this causes is a kind of an inverse effect in its load carrying capacity due to the coordination of making that nut with the ball. There's kind of a limiting factors in that design. So when we look at operating life of a roller screw versus a ball screw, when you consider the same size components, the life of a roller screw can be an order of magnitude higher than that of a ball screw. So a roller screw of half the diameter of a ball screw can have equal or better operating life. What this, the benefit of this obviously is that you can have a smaller package. When you're looking at one application, you can potentially have a smaller package or a smaller screw providing the same force, speed, and life as a ball screw may provide. So when we take a look at the electromechanical actuator packaging and design considerations, the higher load capacity of the roller screw is going to provide a longer life, lower stress levels of the components and the roller contact points in the same package size. So it potentially is going to allow that smaller overall size and packaging with comparable life, if you're using a physically smaller roller screw in comparison with a ball screw, you're going to end up with a smaller package, obviously. So also allowing the ability to have that finer lead of the roller screw also provides a benefit in that you're able to produce the same amount of torque as a steeper lead ball screw may with a reduced amount of torque when you're using that finer lead capacity. And because you're able to go at a higher speed, the motor's able to produce higher speed rotationally, you can get a comparable speed to the ball screw that has the steeper lead. So another piece that we haven't really talked about until now is the ability of converting or inverting the roller screw. You don't end up having any recirculation requirements with a ball screw. Inverting a ball screw is not really, it's possible, but there's many complexities involved in that process, and we haven't seen success of that out in the field. So if we look at taking the inverted roller screw and packaging that up into integrated package, we end up with the long threaded cylinder acting as essentially a motor rotor or an armature, mounting magnets right along the outside of that cylinder, wrapping a stator around the outside of that, and then solidly attaching a shaft and a feedback device. What this does is it effectively limits any connection points, couplings, makes the whole actuator very rigid and direct process of converting that rotary motion into linear energy. So when we look at the package design here, we're taking, again, looking at the roller screw, or the roller screw cylinder is acting as the armature of the permanent magnet motor. You end up having that direct drive system, no transmission. Your space and your size is limited to its smallest package without any extra components or attachments. The rod sealing can be performed with standard hydraulic rod seals and wipers, and rod material could be matched to whatever the chosen application would be needed. So you end up having all of the roller screw components packaged inside the casing or the housing, and then you end up with a package that looks quite similar to many hydraulic cylinders that are out on the market. So it ends up being very small, lightweight, a few joints to seal, very robust style packaging. So when we look at that size comparison of a typical traditional ball screw actuator, is going to have your rear housing with the reverse parallel pulley, belt pulley system or gearing system, and a motor attached over the top. So you end up with that added motor in conjunction with your ball screw there. So if we take a look at the rated force here on this ball screw actuator with a 6-inch stroke, you're at about 750 pounds. You end up with 10 million inches of life. With the roller screw at a 3-inch frame, so we're taking and looking at about a 3-inch frame ball screw and a 3-inch frame inverted roller screw actuator. You end up with a higher rated force, higher travel speed, and also an order of magnitude higher in the average life that you're going to see out of an actuator like this. So overall, in summary, the roller screw technology we believe should be given strong consideration for use in hydraulic replacements and other types of linear technology replacement systems for electromechanical actuators. The large rolling contact area is going to provide an efficient and robust means of converting the rotary motion from a prime mover to a high thrust linear motion. Higher power density package for a smaller, lighter weight and more robust actuator package. And the design and capacity characteristics provide unique size and weight advantage via the inverted roller screw design with an integrated package. So you're also, again, less likely to fracture or jam than a ball screw actuator, more tolerant to the lubrication deficiency, and a much simplified inspection and maintenance process due to the ability to completely unscrew the roller screw from the cylinder or the nut from the roller screw shaft. So with that, I appreciate you listening in on this presentation, and I'll go ahead and hand it back to the moderator.
Thank you, Mike. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen, then hit the submit button. While we are answering your questions, we'd like to ask you to complete the feedback form, which is located on the bottom left of your screen. So, question 1. What conditions cause heavy contamination?
What conditions cause heavy contamination? In the case of the roller screw, it really depends on the environment. So if a roller screw is packaged, your contamination is typically going to be limited to ingress into the screw. That could be if there was a shaft seal that was worn out and liquid ingress came in, causing rust deposits and things like that. That could be a matter of contamination. But typically, outside influences are where you're going to see that contamination come from. So in the case of a packaged actuator, there typically isn't going to be contamination that you're going to see on a regular basis, other than through grease hydration over time, depending on the heat and those sorts of things. So hopefully that answers the question.
Question 2. Are the screws normally ground or machined?
The screws, well, the roller screws themselves, typically roller screws and ball screws both, grinding is a normal process for roller screws. Pretty much all the manufacturers out there use a grinding process for roller screws and ball screws of many types. So that typically is there. There's some other types of ways of doing a thread rolling so you roll the shaft instead of grind the shaft. These are all pretty common in both the roller screw and the ball screw manufacturing techniques.
What is the maximum linear strokes your design can be adapted for?
The maximum linear strokes on conventional roller screws are typically based on the machining capability. There are, me personally, I'm aware of roller screws that get into the 10 and 12 foot long range. They typically go very, very slow. They're typically very, very large diameter and very large force requirements for those very long screws. In a packaged environment, in a roller screw package, typically you're going to see in the 48 inch is probably going to be a typical length. I've seen packaged electromechanical actuators that have gone into the 6 foot range, so 72 inch stroke. So that it really all depends on the supplier and the ability of manufacturing technique for the supplier. With regard to the inverted roller screw design, you're again limited by manufacturing technique, but in this case, you're having to manufacture the inside of a long threaded cylinder. So there's different challenges that you're going to see in length when you're doing an external thread versus an internal thread, and so you're typically not going to see stroke lengths that go much over 18 inches and probably at a maximum of around 24 inches. That's really when you start getting into difficulties in the manufacturing process.
What keeps the output shaft from rotating?
What keeps the output shaft? On a conventional roller screw design package, there typically is anti-rotation in the tube that is going to ride along the shaft, which is your output shaft. So that is input and output. With regard to the inverted roller screw design, part of the installation or the application requirements is going to be having that shaft solidly mounted to a machine coupling or tooling on the machine. Otherwise, providing some sort of external anti-rotation device on that output shaft. There are also other ways of using splines and different types of non-circular output shafts that can allow for different types of spline nuts and things like that that will keep it from rotating. But typically you're going to see that mounted on the machine.
Can these designs be supplied into all industries? Nuclear, petrochemical refineries, for example?
Yeah, so actuators in general, the electromechanical packaging and types of units are really available for really any industry. However, the place where you get caught with really any product when you start getting into industries like a nuclear industry or like certain oil and gas and refinery type industries is you get caught into the certifications and ratings required of any equipment that goes in there. So is it possible to have packaged electrical mechanical actuators, including roller screw actuators, to be certified for those types of environments? The answer would be yes. As far as XLR ourselves, we have some limited products that are available with some CSA, hazardous, ATEX, IECEX certifications for different parts of the world regarding hazardous location or explosion-proof type environment. So they are available. It really depends on the product and the supplier.
How does the backdrive force compare against the ball screw?
Well, backdrive force is effectively calculated, or the theoretical backdrive force is going to be based on the lead of the screw and its efficiency and the amount of force being pushed against the screw to backdrive that screw. So typically with a ball screw, because you're seeing a higher lead, that higher lead is typically going to backdrive a little bit easier. If you're having a finer lead, from physics, you're going to have a harder time to push that back. So depending on what the application is, and if you're comparing a ball screw to a roller screw with two of the same lead, then your backdrive force is effectively going to be very similar depending on the efficiency of each of those screws.
What is the maintenance schedule life for a typical roller screw?
The maintenance schedule for a roller screw is really going to be like any geared mechanical device, whether ball screw, roller screw, or gear head. It's going to be based on the amount of heat that's generated in the application, the amount of degradation of the grease, the type of grease being used, and as that grease breaks down, that timeline of when that grease breaks down typically is what creates that maintenance schedule. We provide some guidelines for our customers as starting points, but we typically recommend that each individual application take considerations for a maintenance schedule that meets the needs of their application. But to give you kind of an anecdotal on that, we've seen repairs of units that have been in applications for 15 years, and when we've asked about grease renewal, they didn't even realize that the unit could be serviced in the field. So, you know, we've had situations like that where they've come, you know, for very, very long periods of time with effectively no maintenance or no grease renewal. But then there's other applications that require grease renewal in very short intervals, just due to the nature of the application.
Can you please provide a cost comparison between a ball screw and a roller screw actuator?
Cost comparison with a roller screw to a ball screw is really a difficult subject, and it's mainly because we have to take into account the pieces that we're comparing to. So if we're taking an application and comparing one application to another application, a roller screw is typically going to be competitive to a ball screw in regards to price, because we can oftentimes use a roller screw that is a smaller size, and typically you're going to see pricing go up from smaller sizes to larger sizes. So if you're using a smaller frame size roller screw and comparing that to a larger size ball screw, your pricing compatibility there is potentially going to be very similar. Now, depending on what the customer's needs are, if they're looking for something with much greater life, then now all of a sudden we're not necessarily comparing an equal product. So we look at that extended life as you may have to buy 2 ball screws in comparison to 1 roller screw. So if you look at that from a value standpoint, you may pay more for a similar frame size roller screw, but you may have to buy 2 ball screws in the same period of time as you'd have to buy that 1 roller screw. So hopefully that helps.
How does a roller screw compare to an hydraulic actuator of equal size and rate force?
That is a little bit tougher question as well. It's going to depend on the application, but a hydraulic cylinder, oftentimes we can create a package at XLR. We can create a package that will be similar in size and similar in force characteristics to a comparable hydraulic cylinder. Hydraulics are always going to have their place in the market once you get into the larger and larger sizes. There are certain frames and mechanics that could, you know, potentially limit the forces when you start to get into the hundreds of thousands of pounds of force and those sorts of things. So there are some limits, but typically package size you can get fairly close with hydraulic versus pneumatic. Or, sorry, I just hydraulic versus the roller screw. I apologize.
This is a question regarding premature wear. If an actuator movement is repeatedly used in one spot, will this bring on premature wear?
I wouldn't say it's premature wear. In the case of an actuator that's run in a single spot, you're effectively using a singular process. When we're using that in an application such as when you're using an application such as a pressing application. When you're using the pressing application, you're going to end up hitting the same spot over and over and over again. So you effectively turn into your life calculation or your theoretical life tends to be less regarded in the number of inches you can travel and more the number of times you can cycle to that same point over and over and over again. So that again plays a role in the life. So we typically do have some derating factors that we use in order to provide our customers with an idea of what the best life they're going to get in pressing or a very short stroke type application.
Can roller screws go up to 50,000 or 60,000 pounds of linear motion?
Yes. The answer to that is yes. The roller screws, the conventional roller screws with a long threaded shaft. XLR has product lines that range from 5,000 pounds all the way up to 40,000 pounds, and in some cases we've done some special designs for customers that go up to 60 and maybe even 100,000 pounds in certain applications. So the technology is capable. It's really a matter of what the manufacturer is able to do regarding packaging that.
What are the maximum operating temperature limits for a roller screw?
The maximum operating temperature limits for a roller screw by themselves are going to be based on the ability for the grease to handle that temperature. So you're very likely, unless you're getting to the melting point of the raw materials, you're probably not going to have much trouble. It's really going to be based on how long will the grease last within that environment. When we shift over to an integrated package design like the inverted roller screw package that we showed, there you're going to have the permanent magnet motor thermal limitations. So in the case of most brushless motors, you're going to have somewhere around 100 degrees C case, 130 degree, maybe even up to 150 degree C temperature range for a servo motor or a brushless permanent magnet motor. So we at XLR for our package design typically recommend maybe up to 85 degrees C in an ambient environment, potentially higher than that in certain applications. It starts to become very application dependent once you get above 85 degrees C in the ambient.
Are there any restrictions in the orientation of operation, horizontal versus vertical, for a roller screw?
There really isn't. It becomes more a measure of what the force needs are in the orientation. So if you're looking at a horizontal orientation that's sliding along rails, you may have a higher inertia if you have a big load sitting on those rails. Whereas if it's a vertical application where you're lifting and lowering a lot of tooling, you're going to take into account that tooling weight. So really the orientation has really no effect on the screw itself, but it could have considerations that would be needed when you're choosing the screw to make sure that you get the right screw for the application or packaged actuator.
Are roller screws multi-lead?
Are roller screws multi-lead? I think what they're talking about there is multi-starts in the screw. Roller screws are going to have each multiple start threads. Depending on the diameter, you could have 3, 4, 6 starts of thread in any given diameter. So the manufacturing techniques allow for making those multiple thread starts within the screw.
Can roller screws be used in applications where high linear stroke speeds are required?
Where high linear stroke speeds are required. Yes, depending on what the definition of high strokes is. Did they give an example?
Yes, the question lists, for example, 24 inches per second moving moving a 1-ton load.
1-ton load, so 2,000 pounds at 24 inches a second. Yeah, that would be a pretty common application that we might come across. So in the integrated package design, you might see speeds that could get up to 40 inches per second. You might see forces that go up to 10 to 12,000 pounds. Now, if you're going 40 inches a second, we're probably not going to be doing 12,000 pounds. We're probably going to be doing more like 4 or 5,000 pounds at a max. But if you're doing 12,000 pounds, you might see a max speed of 5 inches per second in that. And then once you go to the conventional roller screw design where you're adding back that external motor, then you really have a lot more flexibility on power range. You can get a really, really big motor if necessary, and depending on all the application characteristics, you can get a screw going pretty fast while also having a fairly high force, potentially upwards of 10,000 pounds or even 20,000 pounds of force. If you have a large enough motor, you could be going 20 or 30 or 40 inches per second.
And we'll wrap up with this last question. When you calculate the screw life, how is lubrication considered?
The lubrication actually isn't considered in screw life, and that's mainly because we consider that a separate discussion. Maintenance is, we separate maintenance from life. So life is assuming a consistent good lubrication over a period of time. What's the L10 life is typically what we offer, which is 90% of the time you're going to get this life out of the screw. So if a screw is not maintained at all over a period of time, is it possible it could last through its entire life? I would say yes, it's possible. It's probably unlikely in a lot of cases, but in certain cases you could have a situation where the screw would go through its expected life and meet the customer's requirements without having grease renewal.
Thank you, Mike. Well, that concludes today's presentation. On behalf of Machine Design, I'd like to thank you for joining the webcast today, and thank you to XLR for sponsoring this event for us today. Have a productive remainder of the day. Goodbye.